Stud.
Hi, guys.
Stud.
Alright, derivatives of logarithmic functions. Oh
May I take your headset? May I take your headset?
Shut up. That's my pen.
wow. Find the derivative of y equals the natural log of x. So, kind of like why you asked, like, how is this true? Why is this true?
Oh, you never showed me that, though.
I know. I'm going to walk you through, though, the how and the why of the natural log of x using e to the x, since we now know e to the x.
Okay.
So what could I do to change this function so that instead of having an ln of x, we have e's, because we know how to take the derivatives of e's. So what could we do to both sides to start? Yeah, so like if I e, I get e to the y equals e to the natural log of x. What happens to the right side? The e and the ln of x cancel, leaving you with x, and you have e to the y. So you can see in my directions I put, you have to use implicit differentiation. Because now, instead of having y isolated and by itself, y is up in your derivative. So, what's the derivative? The dy dx dx dx. What's the derivative of e to the y?
E to the y times e to the y.
Times, what's the derivative of y?
1 dy dx.
1 dy dx. Okay, what's the derivative of x? 1 dx dx. Okay? What do we have to solve for? So what do you do to e to the y? So dy dx equals 1 over e to the y. Okay?
So do you not actually take the derivative of ln?
We did. What do you know about e to the y?
It equals e ln x. Or it equals x.
So, dy dx equals 1 over x. So what that means is the derivative of the natural log of x is equal to what? 1 over x.
So the proof of it's not as long as the
No, the other one is 0. So it's fair game to say, in general, that the derivative of natural log of x is 1 over x. So again, it's fair to say the derivative of the natural log function, ln x, is 1 over x.
I put it up there. I wrote it. It's on there. I just didn't. I got it.
Okay? So, just like e to the x was always e to the x, and then we had e to the u is e to the u du dx.
Yeah.
If you have a function inside your natural log, so like let's say it was the natural log of x plus 1, then you have to multiply by the derivative of x plus 1. So that gives you this ln of u equals 1 over u times du dx, where u is some other function other than just the letter x.
Did you guys understand that? Shut up. Oh. Hey. That's what I thought.
Okay, so in the case of this example, the inside function stuff, u, would be that x cubed plus 1.
Yeah.
So what is du dx or u prime?
3x squared.
So that means that if we talk about dy dx, it's 1 over u times du dx. So it would be 1 over x cubed plus 1 times 3x squared. Or it's 3x squared over x cubed plus 1. So it's the inside stuff that always goes into the denominator, and then the numerator is the derivative of the inside. So the inside stuff doesn't change. It just becomes your denominator, and then you multiply by its derivative. It's like a chain rule in a way again, but again, the rules are a little different because natural log becomes 1 over whatever the inside stuff is.
Right.
So, what's my inside stuff?
Sin X.
Yeah. So, inside's sine of x. So, u would be sine of x. That means du dx, or u prime, would be cosine x. That means that dy dx is 1 over u, or 1 over sine x, times u prime, which is cosine x. So you get cosine x over sine x, which is cotan. Very good. Okay. Now the next one is a chain rule within a problem. So we have the natural log function inside a function, and this is why we talked about last week, or earlier this week, I guess, cleaning up these types of functions. So this is really the same as saying y equals the natural log of 2x all to the 1/2 power. So, what's the derivative of anything to the 1/2 power? Well, you get 1/2 remain inside natural log 2x. Subtract 1 away from your 1/2, so you get negative 1/2. Chain rule says then you take the derivative of the next inside piece, which would be the derivative of the natural log aspect. So that would be 1 over what's inside the natural log, which is 2x, times the derivative of the inside stuff, so derivative of 2x is 2. Well, what do you know about 1/2 being multiplied by 2? Yeah, it's 1. They cancel each other. So then now we get 1 over 2x, because this is in the denominator, but this negative exponent's also going to drop to the denominator. So you get 1 over 2x square root natural log of 2x. Okay? So here, I treated the entire denominator to be in the square root. I don't know if the notes show it better. So now I have a quotient rule, but this is all inside the natural log, right? So it's the natural log of x plus 1 over the square root of x minus 2. So this is where those natural log rules come into play. If you have a natural log and it contains division, you can rewrite that natural log as subtraction. So you could rewrite this as the natural log of x plus 1 minus the natural log of the square root of x minus 2. And then what's nice here is because that square root's inside the natural log, that's kind of like the same as saying x minus 2 to the 1/2 power. Well, if you have a power inside, you can bring it out as a coefficient. So now I can even turn this into the natural log of x plus 1 minus 1/2 the natural log of x minus 2, and I don't have to do a chain rule.
Sweet.
So now you just apply your rules. So here it's natural log of x plus 1. So the derivative says 1 over the inside stuff, so it'd be 1 over x plus 1, times derivative of x plus 1, so derivative of x is 1. Yep. Minus, remember this is like a coefficient, so that 1/2 sort of tags along, because if you did the product rule, it would zero out anyways. So it's 1/2 times 1 over the inside stuff, times derivative of the inside stuff, which again is 1. So you get 1 over x plus 1 minus 1 over 2 times the quantity x minus 2. You don't got to find a common denominator. There's no need to make that algebraically simpler. This is one of those derivatives that is kind of like a pain in the butt, and you sort of just have to memorize it. But if you think back to a couple days ago when I gave you that change of base formula, I told you that the log base A of x, or in this case log base A of u, was equal to the natural log of u over the natural log of A, right? So that's the change of base formula. This and this are equivalent. Well, if you took the derivative of this, A is never a function. A is always a constant, right? So that's kind of like saying, oh, 1 over natural log of A, where that's a constant, times the derivative of natural log of u. But what do we know about the derivative of natural log of u? It's 1 over u times du dx. So do you now see where this crazy derivative came from? It came from the change of base formula for the derivative of the common log. So this isn't just some like crazy thing that somebody came up with. They actually transformed it by change of base and then derived that, which you can do. That's a valid option, or you memorize this. And if you go back, if you think about it, this right here is just a number. That's not a function. This is a function, and this is a function, but 1 over the natural log of A is a number. Okay, so I actually kind of jumped my own gun and I said use the change of base formula and prove it. Well, I just proved it to you on that same screen, and I kind of like proving it on the same screen because you can see it much better. So now, if you go back to that idea, this is 1 over the natural log of A. So your derivative is 1 over the natural log of 10. So it's whatever the base is inside a natural log in the denominator,
Right.
times 1 over this stuff, times the derivative of this stuff. Yep, so derivative of 2 is 0, derivative of sine is cosine. So you get cosine x over a natural log of 10 times 2 plus sine x. And lastly, this is if you have like a number raised to a function. So now let's say I have like 2 to like the x cubed. You kind of treat it like the e to the x. The a to the u stays. Then you have to multiply by ln of a and then times the derivative of its x there. That one, I don't have the derivation, like where it came from. But this one, you just kind of memorize it together. So, remember, you keep it. Yep. Times the derivative of the 2x, which is, yeah. No. Like, and what you could do is kind of just treat this, it's hard to even clean it up algebraically.
Yeah, 8 seconds.
Okay, homework is in your book.